Basically, before we migrated to Kafka, our in-house PubSub solution is called Event Bus. Event Bus is a PubSub system which is based on Apache Bookkeeper and distributed log. And I believe many of you have already heard about it. And yes, it is pretty similar to Apache Pulsar. And Event Bus, that is because Event Bus and Pulsar, they both use Apache Bookkeeper as the storage engine to persist log messages. Compared to Kafka, Event Bus is different in a way that it has a proxy layer over the storage engine. So in this graph, you can see that we have write proxies and read proxies. So publisher clients, they only talk to write proxies for fan-in write requests. And then those subscriber clients, they talk to read proxy for fan-out. Write proxy actually here helps to manage fan-in connections, string ownerships, and ordering guarantees, batch, and compression. Read proxies here mostly basically serve the purpose of caching, so that when we have like multiple subscribers all reading from the same topic or streams, most of the requests can actually serve from cache. That actually helps to reduce a lot of network IOs to the backend storage layer. And one major benefit for this design is that it provides us the flexibility for us to scale up or down the read and write proxy clusters independently based on our customer need. For example, if there is a string that has extremely high fan out read traffic, but very small in the amount of write traffic, we can put that string into our high fan out cluster, which has a lot of read proxies to better serve that customer. So some of you might be curious, why did we actually make the decision to move from Kafka to Event Bus? So there are a couple of motivations behind this decision. First, Apache Kafka has a very large and active open source community. So by moving to Kafka, we hope that we can get the benefits provided by open source community. For example, like quick iterations, free bug fixes, etc. And since Kafka is so popular, by moving to Kafka, we are also hoping that it would help us to attract more better talents and hire more domain expertise to help us running Kafka at scale at Twitter. And feature and ecosystem are the other two main reasons why we choose to move to Kafka. So Apache Kafka provides us a lot of very useful features for our customers that is not provided by Event Bus at that time. For example, exactly one semantics and Kafka streams. So this actually helps us to increase the development velocity for our team to deliver new features to our customers quickly. And last but not least, from cost perspective, we have actually done some evaluations to compare Kafka cost with Event Bus. The evaluation results tells us that Kafka is able to achieve similar performance as Event Bus do, but with fewer number of machines. So moving to Kafka would actually help us to save some cost. So this is a quick overview of the overall migration approach that we took at Twitter. So we provide our customer with the self-serve ability to basically do the whole migration process. So in order to migrate a topic from Event Bus to Kafka, we first set up the replication job between Event Bus and Kafka so that we will make sure all the incoming events from Event Bus will also be available in Kafka at the same time. And meanwhile, we also provide a migration tool for our customers to being able to dynamically switch the migration on and off. In this architecture, basically you would see that client will talk to both Event Bus provision service and Kafka provision service. But it will first try to talk to the Kafka provision service to check whether the migration flag is on or off. If the migration switch is on, then it will just get the Kafka backend information from provisioning service. Otherwise, it will just fall back to event bus backends. Although the migration process seems simple, there is still quite a few challenges that we have encountered during the migration. First is about the scale. Because in event bus, we have like thousands of topics and subscribers to migrate. So we have to do a lot of work to sort those active and inactive streams and subscribers out. And we also like spend a lot of effort to basically organize the migration priority. And second challenge is about cooperation. Because event bus topics and subscribers are owned by hundreds of different teams at Twitter, and it's used by a lot of different services. And so although we have like provided a self-serve migration tool and a pretty sophisticated runbook, there are still like a few issues that encountered by different teams due to different use cases. So a fair amount of work our team is basically to provide support for our customers to address those issues that they encounter during the migration. And third challenge is basically because migration is very mission critical. A few revenue sensitive like services, they all have pretty strict dependency on event bus. So we have to design the migration in a way to minimize the risk. But at the same time, we also want to reduce the amount of work that needs to be done by both sides. So here you can see this is a high-level like architecture diagram of the current Kafka ecosystem we have built since the Kafka adoption. From top to bottom, first we have built a Kafka self-serve and provisioning service. So Kafka self-serve is a front-end web console for our customer to easily onboard to Kafka, while provisioning service basically is a RESTful API to support that in the backend. Customers use this portal basically to provision and manage their own topics and consumers. And they can also like do some monitoring and capacity planning on that portal. And on the left side, we can see that events are coming from like multiple sources. There are services which they use Kafka producers directly to write events to Kafka in their services. And there are also events coming into Scribe and Flume pipeline first, and then the Flume aggregator will forward those events to Kafka brokers. On the right side there, that is a consumption pipeline. So on the consumption side, we support both real-time processing and batch processing. For batch processing, customers can actually request replication from Kafka to HDFS since we have implemented our own replicator service to achieve that. But still, the majority of our customers are still using the Kafka consumer API to consume events from Kafka brokers. Apart from that, we also adopt Kafka streams as one of our top choices for real-time stream processing. To allow Twitter internal customers to quickly build Kafka stream applications, we actually created a Finatra Kafka stream library on top of our Twitter server, and that is already open sourced. So as we know, Twitter has multiple data centers, and there are customers who basically want the data to be consistent among multiple data centers. So to support that, we actually have implemented our own cross data center replication service instead of using the open source Mirror Maker. There are a few reasons why we chose that in the beginning while we evaluate Mirror Maker, but those might not be applicable to Mirror Maker 2. So first is we want the replication service to be able to support dynamic configuration update so that when customer requests new replications for a new topic, it can automatically be picked up by our replication service without any deployments. And second is we actually implement our replication service in a way that that it can achieve the async event processing, so that it improves the performance a lot. And we also need our replication service to support NDC replication, so that it can replicate events from one DC to multiple remote DCs. Besides the replicator, we also build a filtering service around Kafka topics. So the motivation for that service is basically some customers are only interested in a subset of the events in the topic. And those events usually match a particular filtering rule. So filtering service responsibility is basically to read from the original topics and then generate the filtered events into the other topics, which match this particular rule defined by the customer. Also, we currently are hosting our Kafka Connect application, which replicate events from Kafka to PubSub. And in the future, we have plans to also support Kafka to Kinesis as well. So from monitoring perspective, we have also did some work. We have also done some work to implement an external lag monitoring service called Observer. And the main responsibility of Observer is basically to catch lag when consumers stop consuming or somehow stuck. This is different from the Kafka client's lag metric, because when Kafka consumer stuck or it is not able to consume any events, the lag metric exposed by the client will not be available. So that's why we need to add our own external monitoring service to catch this kind of issue. Last but not least, we have also encountered some of the rebalance issue during our cluster expansion, since Kafka itself doesn't do very well in the auto rebalance mechanism. So we have to basically write our own cluster balancer to automatically rebalance partitions after we expand our cluster or shrink our cluster. So that is a pretty high-level introduction to our Kafka ecosystem. Next, I will hand over to Ming. He will talk more about the challenges and the success stories at Twitter. Thanks.
Hi, this is Ming. Thank you, Ming, gave a good introduction of the Twitter Kafka ecosystem. I'm going to talk about the challenge and the learning we faced after adopting Kafka and moving to Kafka. So overall, we have very successful experience moving to Kafka. However, there's few challenges I think is worth to sharing to the audience here. So, before we share experience, I think it's good to give an overview of what we have, what kind of system we run at Twitter. So currently, our Kafka cluster broker setup is mainly on-prem, bare metal, using Aurora Mesos hybrid mode. So in the future, right now, we are actually working on to move into Kubernetes, both on cloud and on-prem. This is a work in progress. We hope we can share the learning in the future. The broker configuration we have is mainly 4 terabytes or 8 terabytes of SSD. We are also working on support 24 terabytes. We usually set up JVM heap to 5 gig and to 15 gig, depends on the workload. Our page cache is usually around 45 gig. So scale, in a Twitter data center, we have roughly 3 data centers. So in one of them, we have around 50 Kafka cluster. They are average size, it's around 100 brokers. The largest, it's 300 brokers. And overall, we have more than 2,000 topics and 40,000 subscribers. Uh, Currently, in each data center, we have the total throughput is around 120 million events per second. The ingress is 120 gigabytes per second. The the egress is around 900 gigabytes per second. Apparently, the throughput of the read throughput is much higher than the write throughput because we have some large file ratio for certain topics. So we have some topics, they are pretty large. Some of them, just single topic, they have like larger than 3 gig bytes per second throughput. So currently, we have pretty uniform version in both client and broker. That's what we strive to keep the version same and also as recent as possible to help lower the operation and easy to debug issues and also get a newest feature for Kafka. So the version we have currently on broker side 2.5, we are in the progress actually move to the latest 2.7. The client, Kafka client, the Kafka stream we have is 2.41. So for next few slides, basically the challenge and issues are mainly applied to those versions. The first issue we run into when we first move to Kafka is latency sensitivity and for different workload. As Yimi just introduced, explained for our old system called the event bus, which in previous slide you will see the storage layer, the bookkeeper, and the write layer we call write proxy, and the read layer, it's called the read proxy. They are all three different clusters. So they nicely insulate between each other, has good isolation. However, as we know, Kafka, we have this shared storage and serving layer, which is basically the broker. It's the only layer to do both roles. Also, in our own data center, in our own configuration, we usually set ACK equal to wall. That basically means we achieve durability by replication. We for every producing, we basically wait for the follower to act. Due to this kind of architecture, which causing a few apparent latency problem. For example, during deploy and upgrade, we can see whenever we do a deployment, the latency will be affected because there's going to be some catch-up traffic from broker, from follower broker. So what do we plan to basically doing some throttle rate, doing throttle the topic before each broker restart. Another one is about noise neighbor and traffic fluctuation. These actually cause quite a few latency or lag if there's such thing happened. So we plan to add quarter management and rate limiter to avoid that to happen as frequent as possible. And the other one is operation. As you know, whenever you do either cluster expansion, class shrink, or you have to replace the bad broker, basically from a bad machine or bad disk, you're going to basically introduce rebalance, also doing some replica movement. Those will affect other replica residing in the same broker. Also, the read-write interference is another event going to happen because we have some like ML machine learning workload. The fan out ratio is close to 10,000. When I say fan out, I basically mean there is like a 10,000 subscriber reading from the same topic. So this huge fan out ratio causing the read-write interference a lot because the producing will have to wait for the earlier we mentioned we achieve durability by replication. In that case, write has to wait for the follower broker to fetch. Due to this huge read ratio, the fetch is going to be slow. So the write is also slowed down significantly. Another one is it's the one we discover is the network thread in Kafka is follow this round robin scheduling. So, but it doesn't really consider whether the network thread is the incoming connection is long lived or not. So some of connection might be long lived and more expensive, but in certain cases they happen to be scheduled on the same network thread, so causing this imbalance between the network thread processing. So to mitigate this, we usually allocate a much higher number of network threads, like for example, 48 network threads for such workload. Next slide, please. Another issue we run into is producing and consumption. Inside our data workload, we have quite a few producers. Their workload is pretty high. Before the key 480, like a sticky partition come along, we actually invented our own way of using a subset of partition to write and batch traffic. This doesn't work well because it sometimes introduce some imbalance between partition. So I think the keep 480 using sticky partition actually solves this problem very well, and we are very just happy community bring up this to a solution. Another advanced feature we use in Kafka is idempotent producer and transaction producer. The problem we run into is for idempotent producer, as you know, there's a GC on the broker causing that's due to the producer ID cache. Also for transaction producer, we still run into a problem where sometimes aborted transaction is not purged in time, so we have to restart broker. This is the issue we are running into. For the transaction, we're still trying to find out what's the best approach to make it more stable. But overall, I think those advanced features are much more stable and improved in last 2 years. Another issue right now we are working on right now is the lag from rebalance. As all of you know, the K429, the incremental cooperative rebalance, greatly improve rebalance performance and make it less disruptive to all consumer instance. However, even with incremental cooperative rebalance, there are still cases where the rebalance latency it's more than 200, 300 milliseconds. This actually usually fine for majority of our workload. However, we still have some workload who is very sensitive to the end-to-end lag latency. So I think there's still lots of room to improve the overall rebalance latency. That's what we are working on right now. After we adopted Kafka, another thing we adopted is basically Kafka Stream. As you know, Kafka Stream is a real-time computing library built on top of Kafka library. Internally, we have evangelized and asked our customer to adopt that, and they definitely experienced many success. Because Twitter internal is basically a Scala-based code base. So we created this financial-based Kafka Stream wrapper, which help our customer to easily set up, run a microservice, Kafka Stream based on microservice. So we open source this library. You can check it out. There are a few features there. One example of such Kafka Stream workload is has very scalable, which has like a 2.5 gig input. We have a link there. This workload has been blocked in the Confluent blog site. You can check it out. There are some few interesting discussion there how we using a Kafka Stream to solve the internal data problem. We still run into some few limitation of Kafka Stream. The first one I think is already resolved in 2.5. It's used to be the case stream assigner group message size is pretty big. So actually, if I effectively limit the maximum group size, we have to run basically a max group size like lower than 300, 500 internally. But I think 2.5 remove that limitation. Another big limitation is for my stateful workload, we try to ensure the same machine is always assigned. When you run the client on the same machine, you assign the same partition to avoid the state log reshuffle. So we have some internal workaround. I think the static membership part helps solve this part partially, but then not entirely. We still try to work with community to have a better solution to address this. Another problem we run into you quite frequently, maybe not so frequently, but it's more severe, I would say, is a disk failure, which causes unclean data reduction. So we used to run into this more frequently. Right now, I guess since 2.5, due to that configure changing, we probably still run into maybe, I would say maybe once every month. Maybe look at the frequency, maybe it's not too frequent, but I think that's the only event which might causing some potential data loss, because whenever it causes offline partition, is the only solution to get it out is basically you have to set the unclean reduction, which is causing a potential data loss. We have found the Uber also with this keep file one for this problem. We really like to work with community to resolve this issue. So another issue we run into is replica rebalance. As I explained earlier, we have this bare metal machine. So the disk is of course locally attached. So that basically means either if a disk is failure or the machine is failure, you have to take out the machine, swap with new machine, which is going to basically cause some kind of like a disk rebalance or class, or another scenario is class expansion, which, as you all know, the replica reassignment and the move is kind of this like slow process. If you want to speed up, it's going to cause some quite latency impact. If it slow down, it's actually can be quite slow. So in the case of you want to resolve some like a real lifestyle instance, it's not great to have like a slow process. So also you also have to plan ahead, because if the traffic suddenly grow a lot, from like 80% disk utilization to like 90% disk utilization, there's no good solution to quickly mitigate that problem. It's also the other problem is that this utilization can't be too high, because we have to give much higher, like 20% or 30% buffer room to let it grow. Also, for certain platform, we have this multiple disks in one machine. So we've also run into problem where between the disk, there are no imbalance inside same broker. So we have to also rebalance intra-broker. So all those are kind of problem run into. That's why we implement our own rebalancing service to help mitigate such problem and reduce the operation burden. So in the future, we definitely want to separate compute and storage. I think there's few approach there. Maybe they can combine. One is when we move to Kubernetes, we want to definitely explore the network attached volume to reduce this local attached disk. The other one is the tier storage. I think this is the key 4.5, which we then want to work with community to speed up the adoption and the progress on this keep. So this basically concludes the talk. I'm very happy you can come to join our session. Please, if any question, please raise it up.